Welcome, new module, differential equation. You can use for further practice, you can refer to this reference or any similar book you have. If you go to this website, the Groundwater Project, you will find a lot of free books that cover this material where you can do a lot of practice. Okay. Uh, we did differential calculus, we did integral calculus, which are needed as an introduction to differential equation. And differential equation, that will be the last part of our calculus module, which you see here forms a big part of our course. Other part related to calculus, which is numerical integration. I will not do this in this module. I will do it in the next module with computer simulation and modeling. That's where we're going to do the numerical integration because that's related to computer simulation and modeling. Yeah. And then finally would be the linear algebra module. Okay. So it has like two lessons. One lesson will be the fundamentals, and then in the second lesson we will see how to apply these fundamentals to some common problems that we see in water resources engineering and predator-prey model, which is a classical model in differential equation, which has a lot of practical applications, yeah, in water resources engineering and other uh, uh, discipline, not necessarily in engineering, but engineering, economics, and much more. Yeah. So let's start with lesson one, the fundamental of differential equation, and we start this by just doing basic terms. Yeah. So in this part, we will understand basic term of a differential equation, like what is the order of a differential equation, what is a linear versus non-linear differential equation, what is a homogeneous versus non-homogeneous differential equation, what's the difference between an ordinary and partial differential equation, and more importantly, what is a differential equation? Yeah. So a differential equation means that you have a combination of a function and one and more of it is of its derivative. So let's say I have a function y here. Let's say plus 3x is equal to dy over dx. Yeah. So here I have a y as a function of x. So this is my function. Yeah. It's combined with one of its derivatives. That is its derivative. So here, this is called a differential equation. Can we see an example? Yes, we can see an example. So an example would be change in concentration with time is equal to, um, so here it tells me how my concentration is changing in time. The rate of a change of my concentration is equal, this is a decay constant. First order, like this is called like a first order decay term, and this is a decay constant. This basically tells me how my concentration is decaying. So here, how my concentration is changing in time is a function of, so here I have concentration as a function of time. The rate of a change of my concentration with time is equal to how my concentration is decaying according to this first order decay term. So I have a function here and its derivative here. So this is the function, yeah, and this is the derivative of the function. Okay. Uh, and okay, so that is basically a differential equation. Now, there is, you've probably heard this term, ordinary and partial differential equation, ODEs and PDEs. So what is an ODE? So ODE basically like whether you have an ordinary differential equation or partial, whether you have an ordinary differential equation or partial differential equation, that will mainly depend on the how many variables, independent variables we have. Let me show you an example. So here dy over dx is equal to y plus 3x. How many independent variables I have? X. That's the only one that I have. I only have x. So this is an ordinary differential equation. We have seen an example before. dc over dt is equal to negative decay constant time concentration. How many independent variables that I have here? I have here one, which is time. Yeah, here, which is x. Here, this is my dependent variable. This is the concentration, and my time is my independent variable. Here, this is my dependent variable, and this, the x here, that's my independent variable. Okay. So here I have only one independent variable versus partial differential equation, like is equal to partial u partial x. So here I have two independent variable like time and x. So I have two independent variable. Can we see an example? Yes, the advection equation. So dc over dt, how concentration is changing in time, is equal to, this is velocity term, dc over dx, partial x. This is partial, not d. Okay, so how many independent variables that I have here? I have two. I have t and I have x. So here I have only one independent variable, which is t. Here I have only one independent variable, which is x. Here I have like two of them. Yeah, basically this equation is telling you how your concentration is changing as time is equal how your concentration is moving in space. So if your concentration is moving forward in space, that's how the concentration will change in time. It will increase in some location in x, and it will decrease in other location in x based on this term. Yeah, so that's called like a partial differential equation. So it depends on what, whether I have a single or multiple independent variable. Here I have a single independent variable. Here I have a single independent variable. That's why this is an ODE. Here I have multiple independent variable. I have like two of them. Here I have multiple independent variable. I have two of them. Okay. So basically that will the order of the differential equation. The order of the differential equation basically has to do with the derivative, the order of the derivatives that you have. So let me show you an example. Like first order, so dy over dx plus y plus 3x. So this is a first order differential equation. Why is a first order? Because I have a first order derivative here. Let me show you another example of, we've seen this before, partial c over partial x t is equal to negative v dc over dx. So this is a first order differential equation. Why? Because I have first order derivative here. So in this case, like this guy would be like first order ODE, ordinary differential equation. That would be second order partial differential equation, PDE. Yeah, so you will hear these terms quite often among modeler, like is this like an ODE model or a PDE model? So ODE models, this means like the ordinary differential equation, PDE partial differential equation, yeah? Uh, here, this is like a first order. Can we do a second order one? Yes, second order one would be like d square y over d x square. Here, this is equal, yeah? Is equal to y plus 3x. So this is the second order. Why? Because I have a second derivative. I have a second derivative here. So this would be like a second order ordinary differential equation. Yeah. Let's see another example. This guy, partial c partial t is equal to d. This is dispersion coefficient. c over cx square minus v partial c over partial x. What this equation is telling me, how my concentration is changing in time is equal to how my concentration is spreading and how my concentration is moving. So is this and so this is a PDE, but this is a second order PDE. Why? Because I have my concentration here, the second derivative of my concentration here. So I have my dependent variable first order, my dependent variable first order, but here my dependent variable, which is concentration, it is in the second order. So this would be called second order partial differential equation. So this equation is called the advection dispersion equation. This equation is called the advection equation. And this is called the advection dispersion equation. Here, my contaminant in the first one, my contaminant, like in this guy, my contaminant is just moving forward. Here, my contaminant is moving and spreading. So that's a dispersion term. Yeah. Okay. Okay, so we learned a new term now, the order of the differential equation. Let's learn another term. Linear versus non-linear differential equation. So a linear versus non-linear differential equation that has to do with your dependent variable. Like, is your dependent variable like linear or non-linear? So let me show you an example. So a linear, so dy with respect to dx is equal to y plus 3x. So y here is to the power what? It's to the power 1. Y here is to the power 1. So this is linear, this is linear. So this is a linear, this is like a linear first order ODE. Yeah. Let's look at another example. This guy here. The C over dt is equal to dispersion, like how my contaminant is dispersing, advection, how my contaminant is advecting, minus partial C. This is a decay term, so we've seen this decay constant before. This is like a decay, how my contaminant is decaying. So what is this? How can we differentiate? So this is this linear, yes. So C here is linear to the power 1. 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 So what is this? So this is a linear second order PDE, partial differential equation. Yeah. Can we see an example of a nonlinear one? Yeah, we can see an example of a nonlinear one. dy over dx. Is this linear or nonlinear? This is linear because y is to the power of 1, okay, plus equal to y squared plus 3xy. This is linear. This is linear. This is nonlinear because y is to the power of 2. So can we see an example of a nonlinear uh, another example? So here dc over d, okay, dx square negative v dc dx minus k by c squared. So here, this is nonlinear. Why? Because c is to the power of 2. So this is nonlinear. So this is called like a second order decay term. So here I have like a non-linear second order. Why second order? Because I have like the second derivative here. Why nonlinear? Because I have a square here. Partial differential equation. Why partial differential equation? Because I have two independent variable. I have t and I have x. Why this is like non-linear first order ODE. Why this is non-linear? Because I have a square here. Why this is first order? Because I have first derivative here. Why this is an ODE? Because I have only one independent variable, which is x. Okay. Another way to make this nonlinear is I can change this term here, like another source of nonlinearity. So I can say like negative k, for example, sine c. That, like if this term I change it, this term to negative k sine c, that will make it also non-linear. Why non-linear? Because it's a transcendental function. So transcendental functions, this is like exponential function e to the power c, sine c, for example, uh, log c. All these are called like transcendental functions. So if it's so here, for example, this will be nonlinear because it's a transcendental function. Other example of nonlinearity, for example, is that I have uh, the function multiplied by its derivative. Let me show you an example. Like I have d here, dh dx of h dh over dx. Yeah. So here, this is an example also of nonlinear. Why? Because I have the function h, which is a function of x or whatever, is multiplied by its derivative. Yeah. So here, this is also another example of nonlinearity. So nonlinearity means like is like your function is squared, like not to the power of 1. That makes it nonlinear, square, cube, whatever. You have a transcendental function or product of a function and its derivative. So I summarized this for you here. So you can read it like linear differential equation. You need to have the first power, no product of the dependent variable and its derivative, and no transcendental function. Yeah. Okay. Finally, homogeneous versus non-homogeneous differential equation. So this has to do with the independent variable, not the dependent variable. So let me show you an example of a homogeneous. So homogeneous dy over dx is equal to y. This homogeneous, yeah. Let me show you like here, for example, partial c partial t is equal to dispersion partial 2 partial c x square minus v dc dx negative k c square. Yeah, this is homogeneous. Why? Because my independent variable does not appear anywhere, like does not has any separate function here. Okay, does not have any. So here I have how my concentration is changing with time is equal to how my concentration is spreading, how my concentration is moving, and I have a decay term, how my concentration is decaying. So here that would be like that would be like order, second order because I have like the second derivative here, uh, linear, non-linear. So this is non-linear because I have c square here, so that's like non-linear. Homogeneous, homogeneous. Homogeneous because I don't have any source or sink term. I don't have something source function of x or t. That does not exist. Yeah, I don't have this guy. So it is homogeneous and partial differential equation. Partial differential equation because I have two independent variable x and t. Okay. Let's look at non-homogeneous. So non-homogeneous would be something like this. dy over dx is equal to y plus 3x. Now I have this guy here. That is non-homogeneous because it includes an external source or sink term. I have a function here, s, which is a function of x. So I have s of x is equal to 3x. I have this function here. So I can also write this as, I can write this equation as like dy over dx is equal to y plus source term. I have a source term here. Yeah. So I have this source term or like term representing like input injection or extraction or whatever. Okay, so this term here, like you see, this term here represent the decay, but this term here represent like ejection or extraction or something like that. Yeah, so this is non-homogeneous. Can we see an example for this? Yes, we can see an example. So I can here, okay, this brings these two together. So you see the difference between these two. Let me delete this guy. Let me delete this guy. Let me delete. So you see this equation? I will write now a non-homogeneous one. Yeah, dx squared minus v dc dx minus k c squared plus source and sink term, whatever that function is, xt. So now see, I have an extra guy here, which is a function for my independent variable x and t. Okay, so how would I classify this? The same as here, second order. It's non-linear because I have c squared here. It's like non-linear. It is non-homogeneous. Why it's non-homogeneous? Because I have a source and sink term here. And partial differential equation because I have two independent variable, which is x and t. Okay. So that's basically like if you know that, I mean, you know like now the how to classify like this equation and why this is important. Like why learning this thing is important. Learning this is important because this will tell us how can we solve these equations. So that will tell us for some of these equations, they might, if it's not homogeneous, if it's not linear, they might not have analytical solution. And then when they don't have analytical solution, what does this mean? This means that we need to solve them numerically, basically. We need to find numerical solution, which we will be doing in the next module uh, about modeling and simulation, where we'll be doing this numerical solution. Yeah. But that's basically the why this is why like learning these things is important. So let's see an example here. Let's see how we are doing in time. I think this lesson is important, so I can take more time. Yeah. So basic of differential equation. What defines the order of the differential equation? The number of variables involved. No, number of variables involved that will tell you if this is an ODE, if you have one variable, or P D uh, E if it has one independent variable, yeah, and PDE if it has like more than one independent variable, like X and T, for example, yeah. The highest power of the dependent variable. No, the highest power of the dependent variable, like c squared, for example, that will tell you whether this is linear or non-linear. So this will tell you whether this is linear or non-linear. The highest derivative of the dependent variable. Yes, that's basically what it is. So if I have dy over dx, that is like first order. If I have d square y over dx square, that is like a second order. Yeah, that's a second order. The number of terms of the equation, that will just tells you just basically tells you the number of the term of the equation. It has nothing to do with the orders. Yeah. So let's do another one. Which of the following is an example of a second order differential equation? So this is the first order. I have a first derivative here. It is non-homogeneous because I have this source term here. This is the second order, yeah, because I have the second derivative here. So this is wrong, this is correct. This is the first order here, so this is wrong. This is the first order here, so this is wrong. So the correct answer here would be number B. Yeah. Let's do. Which of the following equation represent a nonlinear differential equation? So Let's look here. Nonlinear. This is nonlinear because I have a transcendental function with respect to my dependent variable. So I have dependent variable y, and I have a transcendental function. So uh, this is it tells me this is nonlinear. So this is wrong. This guy is nonlinear. Yeah. So here this is nonlinear. How about this guy? Here I have a function, my dependent variable multiplied by its derivative. So this is wrong. This is like non-linear. So this is linear, yeah. Like here, this is linear, but this is non-linear. This is non-linear because I have my function and its derivative. This is non-linear, so this is wrong. How about this guy here? So this guy here is linear. This is non-linear because I have a square. I have y square, so this is non-linear. Yeah. So this is wrong. How about this guy here? This is linear. This is linear because C here is linear, C here is linear, C here is linear, C here is linear. So this is the correct answer. So the correct answer for this one should be D. Yeah. Let's look at more practice problem. What distinguishes homogeneous differential equation from non-homogeneous ones? And read the question carefully. Because I notice like in your homework, you don't read the question carefully and you rush through the answer. I'm telling you what distinguishes it. So what distinguishes it means that there could be some correct answers here, but they don't distinguish homogeneous from non-homogeneous. So basically, when you select the answer, you select the answer. Like if you find a correct answer here, but does not distinguish between these two, then don't select it. Yeah. So homogeneous equation have no external forcing function. Exactly. So homogeneous equations, they have no s, for example, of xt, for example. Yeah. So that's a distinguish. Homogeneous equation always include variable x. They could include variable x, they could include variable y, they could include any variable. So that does not distinguish these two. Non-homogeneous equation don't involve a derivative. They can involve whatever they want to involve. You have a function, it can involve whatever, or an equation it involves, but that does not distinguish it. Yeah. Homogeneous equation contain constant term. Well, homogeneous equation contain constant term. That's true, yeah, but so is non-homogeneous equation. So that does not distinguish it. So that is wrong. So read the question carefully. The keywords here, I'm not telling you select the right answer. I'm telling you select what distinguish this guy from this guy. So before you rush to the answer, make sure, so the answer here would be, so make sure you carefully read the question and understand what the question is asking you. Okay? Let's do one more practice, I think. Which of the following equation represent a non-homogeneous differential equation? So non-homogeneous differential equation means I should be looking for a source and sink term. Here, yes, I have this source term. I have like s of x is equal to 3x. So this is non-homogeneous. Yeah, this is non-homogeneous. How about this guy? No, I don't like. This is my dependent variable, and this is my dependent variable. Remember, non-homogeneous has to do with your independent variable. Yeah. So this is homogeneous. Yeah, this is homogeneous. How about like this guy? This is my dependent variable. This is my dependent variable. So this is homogeneous. How about this guy? This is my dependent variable here. This is my dependent variable here. This is my dependent variable here, and this is my dependent variable here. This is a decay term. This is a decay term. Not if this is not like a function of x, uh, uh, not like this is a decay term. So this is also homogeneous. Yeah. So basically, this is wrong. This is wrong. This is wrong. So that would be the answer. Yeah. So okay. Uh, let's do, and if you understand this, then your homework problem should be trivial. Okay, so see you in the next video.